Hello everyone, my name is Stephen Lynch and I want to thank everyone for joining me today. In this presentation, I will introduce you to the novel subject of High Visual Resolution Interpretation, or HVRI for short. At the start, this webinar is only a primer to a very complex subject. HVRI introduces new sciences and technologies that I predict will significantly impact exploration. I cannot cover it all in 60 minutes. Consequently, I have developed an 8-hour workshop on HVRI. In it, students will learn the theory and practice of HVRI by studying seismic data from basins around the world. The workshop is run online using Microsoft Azure virtual machines. I'll talk more about it at the end of the webinar. For now, just realize that this webinar only scratches the surface of a new discipline. To begin, HVRI is based on a software product called StratiScape. This is an example of a StratiScape project window. StratiScape is standalone 3D animation software for seismic interpretation. Its primary purpose is seismic visualization. It replaces conventional seismic displays everywhere they are used, and it changes seismic interpretation by introducing high visual resolution interpretation, or HVRI. While it is a standalone application, its full potential is unlocked when connected to Petrel through a plugin architecture. Through the plugin, you can transfer seismic data to and from Petrel, transfer horizons to and from Petrel, and open StratiScape windows directly from Petrel windows. Most importantly, however, interpretations between StratiScape and Petrel are fully synchronized in real time, as is animating through 3D volumes. StratiScape is something new. It does not replace any existing software. Instead, it complements existing interpretation workflows, letting you work in your conventional interpretation software and seamlessly in StratiScape. Since I will discuss high visual resolution interpretation, I will first show you what low visual resolution interpretation is, and then second, I'll show you how to switch to high visual resolution interpretation. You perform a low visual resolution interpretation by interpreting in this type of environment with this type of display. How do you switch to a high visual resolution interpretation? Well, in Petrel, it's easy. Click the single button on the appropriately named StratiScape tab. This is a StratiScape display. It replaces static two-dimensional seismic images from the 1960s and 1970s with dynamic three-dimensional seismic surfaces generated using modern 3D animation technology. StratiScape is a new way of looking at and interacting with seismic data. It does not change the seismic data in any way. It only presents it to the viewer in a more modern format, allowing them to instantly perceive a wealth of subsurface detail that was always present in the seismic data, but filtered out by conventional seismic displays. StratiScape changes the nature of seismic interpretation, taking it into the domain typically reserved for seismic reprocessing. That means that typically, if a seismic interpreter needed better seismic data, and let's face it, they always do, they would not seek it directly from their interpretation program. They would reprocess their existing seismic data and reload it. But I will prove that with StratiScape displays, they will look to them before considering whether to reprocess. You'll agree that there's much to prove in less than an hour. First, I will present a single statement and ask you to remember it throughout the presentation. Whenever we increase the amount of subsurface information available to seismic interpreters, they find more reserves from smaller targets. That short statement defines what we are trying to do. From the time we began using digital seismic data until today, and for decades into the future, we have always looked to increase the amount of subsurface details available to seismic interpreters. If we do, we know that they will find more reserves from smaller targets and potentially from overlooked resources. But before I talk about StratiScape, let me tell you a little bit about myself and how I came to focus my career on seismic visualization. To begin, I am primarily a physicist. I earned my undergraduate degree from the University of Guelph in 1975, majoring in biophysics and minoring in nuclear physics. I graduated as the top student in all science disciplines. I received my master's degree in geophysics from the University of British Columbia in 1977. My PhD, in which I developed the theoretical underpinnings of StratiScape, combined biophysics and geophysics. I received it from the University of Calgary in 2008, and yes, if you're into numbers, that is 31 years after I got my master's degree. My early career was in seismic processing, and in the mid-1980s I managed several processing centers, including Western Geophysical's Calgary office. However, I've spent most of my career in research and development, developing applications for refraction statics modeling, migration, and structural and stratigraphic modeling. But in December 1999, while experimenting with the then emerging graphic cards, I stumbled into this image of a seismic line over a pinnacle reef in northern Alberta, and the focus of my research changed. This image, and others like it, convinced me that there was value in studying seismic visualization. Consequently, I switched focus, and in 2008, I became the only geoscientist in the history of exploration to obtain their PhD in the subject of seismic visualization. In my PhD research, I traced a photon from when it entered the eye to as far into the visual system as we could go at the time. I did that to learn how we communicate visual information, and what I discovered serves as the theoretical backbone for StratiScape. What has emerged from my theoretical research and my extensive examination of seismic data from basins around the globe is that we, in exploration, have a universal problem. The problem is that all wells being drilled today carry unacceptable and now avoidable levels of risk. As a corollary to this, we aren't drilling enough of them. As I will show, the new StratiScape Petrel pathway will help solve both those problems. Why will they? Well, that was a bold statement, but behind it are facts that I began to uncover during my PhD research. To understand why StratiScape Petrel combination is so important and so powerful, I must take you into that research. I'll begin by stating my most important conclusion, specifically that seismic interpretation is a visual science. Regardless of the mathematical processes you use to process your seismic data, interpreting it comes down to looking at it and making decisions based primarily on what you see. We can all agree on that. Although we've now moved on to AI and other technologies, the foundation of any exploration project is what geoscientists learn by simply looking at their seismic data. The problem is that seismic visualization, the science and technology of analyzing seismic data, has been moribund for 40 years. This display is from 1979, and I should know, because I was the first in the industry to produce one. Amoco developed this display in the late 1960s. Seismic has progressed by leaps and bounds since then, but read any geophysical journal or visit any client and you'll see displays like this. Hopefully we agree that our ability to visualize seismic has not kept pace with our ability to acquire and process it. This is what emerged from my research. All the seismic in the global seismic library hold vast amounts of unseen and uninterpreted subsurface details. It is a universal problem. Whether a geoscientist interprets seismic in Petrel or any of its competitors, they are using seismic displays from before many of them were born. Those displays are not up to the task of displaying modern seismic data, not in Petrel or any other interpretation software. As much as this is a problem, it is also a tremendous opportunity because incorporating StratiScape into an interpretation workflow will instantly reveal those missing details. No reprocessing is required. It will also reduce the risk of drilling a well because today, when a company drills a well, it uses a small subset of the available subsurface information. These are the problems the entire exploration industry has today. Companies are missing potential targets and drilling wells with too much risk, simply because our seismic display technology is mined in the 1960s and 1970s. High visual resolution interpretation answers the technical question, how do we see every subtle subsurface detail in our seismic? Getting access to those details solves the practical problems that first, our drilling success rate is too low. Second, we aren't drilling enough wells. HVRI is based on StratiScape displays, so for the following few slides, let's look at StratiScape displays in more detail. StratiScape displays are a breakthrough technology because they solve the problem of how to visualize seismic data so that every subtle subsurface feature is easily visible. StratiScape displays are the theoretically correct way to look at seismic. They ground an interpretation with objective seismic knowledge, and they make all the seismic in the global seismic library worth looking at again. This is a StratiScape display of an inline from the Hibernia 3D. Technically, it is a three-dimensional surface with seismic amplitudes forming the terrain. StratiScape creates this display in real time on the graphic card 60 times per second. The result is a new way of looking at seismic, and if we invented seismic today, it is how everyone would look at seismic all the time. That is an important point to remember. This is how many geoscientists look at their data today. But I invented this display in 1979. I used color because it was the only media available to me, and the interpreters hated it. I can tell you as a fact that if modern GPU technology was available at the time, I would have developed this instead. To reinforce that point, I will zoom into the display. Look at the complex amplitude details in this 3D. Imagine you were interpreting the 3D and that this was your standard display. Would you then choose to display it like this? Admittedly, the colors make this a pretty image. Artistically, it is pleasing to look at. But we are not into art when we're interpreting seismic data. If I move back and forth between the two displays a few times, you will see that this display is little more than a cartoon image of a seismic line. I developed both displays, so I have a right to say this. This one is nothing more than a pretty square wave display, and it should just go away. Following the same logic, what about grayscale displays? Here I've suppressed the amplitude structure so you can see the fine scale details better. Would you replace this display with this grayscale display. Again, I'll go back and forth a few times. And now with the full StratiScape display. Can we display the information here using a few dull shades of grey? No, we can't, but we try to. Daily, seismic interpreters use variable density or grayscale displays to look at their seismic, not realizing they only see a tiny part of it. So now we arrive at the essence of the problem. What are the consequences of using those archaic displays? And what opportunity does still using them hand to every oil company in the industry? So let's change tack. Things seismic interpreters never say. This seismic is good enough. We do not need to improve it. I can see everything I need to see, and I don't need to see anything else. I have a neighbour who is the exploration manager for a company in Calgary. He complains that geoscientists always want to reacquire better data or reprocess their existing data. Seismic, he says, is never good enough. We can agree that this is a universal statement. Seismic is never good enough. We always want better. So how do we get it? Typically, we have two approaches. We can reacquire better seismic, which would cost tens of millions of dollars and require years of planning and execution. We can reprocess our existing seismic, which would cost millions of dollars and may take a year or more. In both cases, you will not know if you've improved on what you have now until you've spent all that time and money. Even if you do improve your data quality, you do not know at the start if you will find anything in the new data that you didn't find in the old data. It is important, however, that a company does get better seismic because if an area has a working petroleum system, there are guaranteed to be overlooked resources. But it's unlikely that anything new will emerge from examining the same data in the same way. Something must change before it's worth re-examining old areas. But as I said, reacquisition and reprocessing are time-consuming and cost-prohibitive. So every exploration company has a vast store of potentially overlooked resources that are not being exploited because of the time and money required to pursue them. This is where high visual resolution interpretation comes in. HVRI gives companies a reason to re-examine their existing projects regardless of the seismic vintage. That is because StratiScape gives instant access to an overwhelming amount of pre-existing subsurface information that conventional seismic displays filtered away. Let me expand on that concept. I am trying to keep this talk as non-technical as possible. However, I must make a point here, so please bear with me. I want you to think about seismic displays in a different way. I want you to think of them as filters, acting on the data like a bandpass filter might. Let me show you what I mean. Here I have zoomed into an area of the line and I'm showing you the seismic using a variable density display for familiarity. This is the same data, but I bandpass filtered it, and if I go back and forth a few times, it's easy to see that the filter has removed valuable information. Because I am using the same display style between the unfiltered and filtered data, it's easy to see that we've removed information. But now I'll do a different type of comparison. I will compare the same unfiltered seismic, comparing first this StratiScape display, with this conventional variable density display. As I switch between the two displays, do you notice how the amplitude details in this region disappear on the variable density display? They are still present in the seismic data, but you lose your perception of them as you do many other features visible on the StratiScape display. Do you get the point? We are using different displays, so the idea that one is filtered over the other is not immediately apparent. But going back to the variable density display, the information in the seismic has not been filtered, but the visible and therefore interpretable information definitely has. The same is true for grayscale displays. Here I have moved to a different line area and removed the color from the StratiScape display. What would you say you did by switching to this grayscale display? Again, I will alternate displays. Watch as details disappear on the grayscale. This simple exercise leads to an inescapable and shattering conclusion. Whether you interpret in Petrel or any other interpretation package, displaying the seismic data decimates the quality of the data. Despite how uncomfortable that statement is, it is undeniable. Whether you interpret in Petrel or any other interpretation package, you only use a tiny subset of the available information. Despite their familiarity, each of the three conventional seismic displays filters away a different subset of subsurface details. That is why I call them low visual resolution or LVR displays. StratiScape displays, by contrast, are high visual resolution displays. They are the theoretically correct way to look at seismic data. They show every fine scale detail, every subtle amplitude variation, and they bring back character and waveform interpretation. And, for reasons found deep within the human visual system, using them in an interpretation grounds the interpretation with much needed objective seismic knowledge. StratiScape displays are an important emerging technology because they prove that all the seismic in the global seismic library contains a vast treasure trove of previously unseen and uninterpreted subsurface information. Having talked about what high visual resolution is and what its impact on exploration is likely to be, now we will turn our attention to a matter of fundamental importance. Specifically, discovering what seismic looks like in its natural state as a three-dimensional surface. Before we jump into the examples, I'll make the point that I can only spend a few minutes on each example. Each example is at least a 1-hour presentation in itself. We don't have that much time, so I'll expand on each example in a series of videos to be posted on my LinkedIn channel. As I go through them, keep in mind that what you're trying to do is become familiar with what seismic data looks like in its natural three-dimensional state. I began my initial work on visualization in the early 2000s. At the time, I knew little about the subject. My PhD was ahead of me, and I did not immediately realize the significance of what I then called StratiScape displays. I only had a few isolated fragments of seismic lines to work with, and while they were interesting, they were not career-changing. I was about to drop the project, but then Peru Petro opened its seismic library to the public, and I came into possession of this project. Eventually, the smallest line in the project, the one shown in yellow, changed everything. I'll open the line and show you what got my attention. I've opened it in grayscale because that's how I initially viewed it, and if you were working on the project, you'd likely do the same. I won't discuss the entire line, instead I'll focus on this area in the upper right quadrant. Notice these tiny events that could easily be misidentified as coherent noise trains. Watch what happens to them when I switch to a StratiScape display. See how they go from potentially easily ignored noise trains to delicate fault plane reflections. Watch what happens to these tiny events as I rotate the direction of the lighting. Notice how they become more and less prominent as the light strikes them from a different angle. I'll rotate the display to focus more on what I realized were fault plane reflections. They cannot be noise trains because I could plainly see they stop at this series of faults and they do not have the same expression as noise trains anyway. Those tiny faults may only be important if your engineers had to drill through them. But if they did have to drill through them, they would need to know they were there, and they probably would not get to know that if this is all you had to go on. I could spend the rest of the day pointing out details on this image you would never have seen on the grayscale display. All I will say is that this image convinced me that visualization was important, and it launched me in a new direction that, through many twists and turns, has brought me here today. If you want to examine this line or the entire project yourself, it is part of our publicly available research projects. For my second example, I will move northeast to the east coast of Canada. The Cupids 3D is a new project for us. We only received the seismic data a week ago. It was shot in 2011 for Statoil Canada and is located on the Flemish Cap. I have both the PSTM and PSTM versions. Either one would do for what I will show, but I chose the PSTM version because I prefer working in depth. Here I've opened an inline from the 3D in Petrel. I'll open it in StratiScape to show you that the StratiScape Petrel connection works for 3Ds and 2Ds. I've opened it using the same variable density display that I used in Petrel. I did that because before I show you this inline as a StratiScape display, I want to highlight a significant problem with representing seismic amplitudes with color. The problem is the lack of available dynamic range. I'll show you what I mean. Color. This is the target zone for this survey. I'll zoom in so we can examine it in more detail. Yellow represents high amplitudes using this palette, which is the Petrel Seismic Default palette. There are many variations present because I've set the amplitude range of the color palette to this specific area. The problem is that the color range, whereas it may be appropriate for the zone of interest, does not work for the rest of the section. There are entire zones with little, if any, amplitude discrimination. If I now set the amplitude range to work for the dead zones, the colors become saturated in the zone of interest. This is just one of the problems with trying to use color to represent seismic amplitudes. The dynamic range of the seismic far exceeds anything we can represent with any color palette. The other problem, as I pointed out earlier, is that when you interpret using a variable density display, you are not interpreting seismic amplitude. you are interpreting blobs of color. This is what the amplitudes look like. Did you expect to see this much detail? I'll go back and forth between the StratiScape and color displays. Did you expect to see this much amplitude detail when you initially looked at the color display? This is one of the major drawbacks of interpretation workflows today. Seismic interpreters are aware of high and low amplitudes, but they have little true understanding of how high and how low the amplitudes are. I will zoom into the main target region. Again, as I move back and forth, notice how complex the amplitudes are and how you lose the sense of that complexity when you switch back to color. That loss is even more apparent when I switch to our dual polarity display. In this display, the greenish colors are the negative amplitudes. There is as much detail in them as in the positives. Again, you lose that detail when you switch to color. I have a final point to make that harkens back to my point about dynamic range. Some zones are uninterpretable whether you work in color or grayscale because they do not fit the range. However, with StratiScape displays, event interpretability is not affected by amplitude. As you see, these low amplitude zones are just as interpretable as the high amplitude zones. Although the zones may not contain commercial reserves, you still must drill through them. What effect, then, does StratiScape have on your ability to identify drilling hazards? Interpreting character and waveform, which served as the basis for all seismic interpretations in the pre-workstation era, is a lost art. The problem is that wiggle trace displays need a lot of real estate, often whole hallways, to be effective. When we entered the workstation era, they were all but left behind and character and waveform interpretation fell out of practice. As I will show you next, however, character and waveform interpretation is about to mount a comeback. Going back in time to 1979, all seismic looked like this. Wiggle trace displays were all we had. They were suitable for one-dimensional character interpretation. As you can see here, they did an excellent job of it. However, they were not good enough for seismic amplitude interpretation. I was tasked with developing a seismic display that would show amplitude better. I came up with this pixelated display. It did show amplitudes better, but the interpreters, skilled at interpreting wiggle trace displays, decried its lack of character. They refused to use it until they were forced to do so by the evolution of workstation technology. Over time, we developed better color palettes and smoothed my initially pixelated display. Not much progress for 45 years. What we have not done is restore character and waveform interpretation. Until now. I will morph back and forth between this StratiScape image and the original wiggle trace image. Unfortunately, it is not a perfect comparison because StratiScape displays need an expanded vertical scale to be effective. But as I move back and forth, you should still be able to understand how StratiScape displays restore character interpretation. Here, I have rotated the display around the x-axis so you can see the amplitudes better. Now with the dual polarity turned on. Finally, as a throwback to the days of yore when seismic sections were hung on walls, here is a dual polarity display, now at an appropriate scale. I want to spend hours showing you the character changes that are now visible on this display, but we do not have the time. Hopefully, however, I've made the point that character and waveform interpretation is once again an essential skill. For my final example, we move to the UK section of the North Sea. The line we will examine is the one in yellow. This is a long and structurally complex line, so we'll only look at a small area of it for clarity. Even though this is only a subsection of the entire line, there's enough here to keep anyone interested in seismic busy for a year. I will quickly show you what the section looks like in variable density and grayscale displays before focusing on three areas. The first are these depositional features here. The second is the unconformity here. And the third is this amplitude buildup over here. So this is the low visual resolution variable density display. This is the low visual resolution grayscale display. I can discuss the theoretical difference between low and high visual resolution seismic displays all day, but these simple comparisons say everything that needs saying. The information content in this display dwarfs the other two. Believing that I've made my point, I won't do any more comparisons. I will show you some focused images and let you gain an appreciation for how majestic the seismic data really is. Focusing on the cliniforms, I don't know what to say other than to admire the intricate bedding detail. There is an amplitude buildup at the top left center. I'll show you here. I don't know if it's significant, but it's what they're looking for in this area. The fine scale details that I see in this image fascinates me, especially little details like this. I hope it conveys that seismic contains much more information than we're used to seeing. Focusing now on the unconformity at the base of the tertiary, I will rotate the lighting around a 360-degree circle. I've not discussed light direction to any extent, just be aware that it is an important element of visualization. Finally, there is a fault visible here and an amplitude buildup at the top where it intersects the unconformity. Whether the buildup is significant is a question, but amplitude buildups against faults are always relevant, so who knows? That brings me to the end of my examples. I want to show you more because I have fascinating seismic data from many other basins worldwide. They will have to wait for another day. For now, I hope these few examples make my point, that the seismic you have is better than you think. To summarize, I will go back to my main point. StratiScape displays are an important emerging technology because they prove that all the seismic in the global seismic library contains a vast treasure trove of previously unseen and uninterpreted subsurface information. By introducing the technology and practice of high visual resolution interpretation, StratiScape displays, without reacquiring or reprocessing existing seismic data, make all that previously unseen subsurface information instantly available. What that means for the future of exploration remains for us to see, but one thing is certain. Throughout the history of exploration, every time we have increased the level of subsurface detail available to seismic interpreters, they have found more reserves from smaller exploration targets. I will sneak this in here because I don't want you to think that HVRI is only valuable for interpretation. Being from a seismic processing background, I know that HVRI is as important to processing as it is to interpretation. For example, high-grading projects is one of the first advantages of HVRI. Seismic reprocessing always improves the quality of the data, but it requires a major commitment of time, money, and resources. Which of the many projects a company has deserves the attention? Examining them first in StratiScape can help companies develop high-grade projects, allowing companies to focus on the ones with the most potential. But getting back to interpretation. StratiScape displays expand the role of interpretation. When companies consider improving their seismic data, they do not currently look to do it through their seismic interpretation software. With HVRI, they will. Interpretation now takes on the role traditionally reserved for seismic reprocessing, increasing the value of a company's seismic data many times over. HVRI is a vital and long overdue new approach to interpretation, and it is unique to StratiScape. So finally, thank you all for attending this presentation. High visual resolution interpretation is a fascinating emerging subject. I only had time today to briefly touch on important and complex topics. To learn more, sign up for one of our workshops. They're run online via Microsoft Azure virtual servers. You will enjoy the workshop, and it will change your perception of seismic forever. Who knows? It might also change your career path. It certainly did mine. So yes, dream big. I understood that there's been a lot to take in here. There are new and bold ideas, but I am confident that if you go over what I've said, you'll see the logic in it. There is nothing small about this. StratiScape may be a simple program on the surface, but it introduces high visual resolution interpretation, and HVRI changes seismic interpretation forever, with massive ramifications. To end, thank you once again for attending this presentation. I hope it has got you thinking. To learn more about HVRI or to get more details on our workshops, either email me directly, message me on LinkedIn, or go to our website. Thank you again.